Okay, great. Good morning, everyone. Welcome to the ECE Colloquium. Today, it's my pleasure to have one of our own faculty members talk about the exciting work they're doing here in the electrical engineering department. Sreeram Kannan is currently an assistant professor here at UW, and he received his PhD from University of Illinois at Urbana-Champaign in 2012. Then he did a postdoc at Berkeley for a couple of years and then joined University of Washington. He received a lot of awards, including the UW ECE Outstanding Teaching Award in 2019, the NSF Career Award in 2017, the Outstanding Dissertation Award from UIUC in 2013, and as well as several awards from Colloquium, including Cognitive Radio Contest First Prize in 2010. His research interests include applications of information theory and learning to blockchains, computational biology, and wireless networks. So it's my pleasure to introduce Sreeram, and I'd like to just ask the audience to please stay on mute during the talk. If you had questions that are clarification questions, feel free to raise your hand and you'll be called upon to ask your question. But for any longer questions, there will be time at the end for discussions. Okay, thanks. And Sreeram, take it away.
Yeah, thank you. Thanks so much, Mariam. Thanks to the department for inviting me for this colloquium. Let me share the screen. Okay. So in this talk, I'm going to talk about how blockchains can be made efficient and scalable. This is joint work with David Shea and Pramod at Stanford, along with many, many others who I'll point out as we go along. Okay, so why are we interested in blockchains? I would like to first point out that we live in a world of digital intermediaries. You look at Google, Facebook, they all connect different players as a digital intermediary. Think of Uber. It connects the taxi driver with the ride hailer, Airbnb, Netflix. They all connect different players in a digital ecosystem. Digital intermediaries have made our life way more convenient, and they run the modern economy. A key feature of them is to aggregate information and create network effects, connecting different people. However, a key bottleneck is they create a single point source of power, and this has been exposed in some of the different areas, for example, the Cambridge Analytica scandal. So one question we would like to ask is it possible to use distributed computing methods to actually solve this problem? So I want to point out that distributed computing is a very classical field in computer science, starting with the distinguished work of Leslie Lamport, and here is the famous book of Nancy Lynch. And the paradigm there is that there are M nodes organized into a distributed system, and the computation is done in a shared manner through the system. However, it requires a permissioning entity. Some node needs to decide who are these N nodes. Anybody cannot come and join the party. So a breakthrough in this space is really Bitcoin. Bitcoin allowed the possibility of permissionless networks. Give me 1 second. There's some problem with the slide timing. Okay, so sorry about that. So you have a blockchain, which is essentially a permissionless network. There is no single node controlling who can participate in the network. This was really the breakthrough ushered in by Bitcoin. So we can see many applications, and I think the most popular application most of us are familiar with are the cryptocurrencies like Bitcoin itself, and the emerging application, for example, Libra is a cryptocurrency launched by Facebook. There is a proposal that in the coronavirus stimulus bill to launch a digital dollar, which is a blockchain-based currency. So, however, I want to point out that the paradigm of blockchain goes far beyond currencies. To organize any digital cooperation problem without having an intermediary. this is the fundamental role of blockchain. Can we get people to come and join the network and without any digital intermediary while providing secure services? Okay, so I'm going to take a reprise and look at what the scorecard is of Bitcoin. So what do I mean by it? The single most striking feature of Bitcoin is it has been in the wild for the last 10 years and withstood hacking, attacks, all kinds of things. And the main reason is that it is resilient to 50% adversity. What do I mean by that? This is going to be a recurrent theme in the talk. What that means is as long as the adversary or bad nodes control together less than 50% of the computation power held by Bitcoin, the network is guaranteed to be secure. While this was not proven in the original Bitcoin proposal by Satoshi Nakamoto, who we don't know who that person is, but it was later proven in a beautiful paper called the Bitcoin Backbone Protocol by Yuan Gare et al. In 2016. Okay, however, while security is a stellar feature of Bitcoin, achieving it in a purely distributed manner, there are other features which are not so desirable. Latency, for example, when you put in a transaction, it takes several hours for the transaction to get confirmed. So this is undesirable. Energy efficiency. So as soon as I announced this talk, our colleague Daniel Kirshen emailed me saying, hey, I'm going to call you out on the energy wastage created by Bitcoin. Indeed, and you see here that it is wasting nearly the same power as what's used in Switzerland. So that's not a desirable feature either. And finally, the throughput, even after using so much energy, you may think it's going towards some computing. It's not. The entire throughput of the Bitcoin network is only 10 transactions per second compared to Visa, which is 10,000 transactions per second, to the New York Stock Exchange, which is 1 million transactions per second. This is really not ready for scalable applications. Okay, so what I'm going to do now is to give a primer on how Bitcoin works. Okay, so I'm going to use the word Bitcoin, but basically what I mean is the fundamental structure of permissionless blockchains. And since it was first proposed in Bitcoin, I'm just going to give them the credit for it. But all I say has nothing to do with cryptocurrency or to a particular Bitcoin. It's a broad applications to any blockchain. Okay, so how does this blockchain work? So I'm not going to assume many of you have heard of this before. So here's how it works. It's a blockchain, so it's a chain of blocks. Okay, so that's that much simple. So each of the blocks you think of as a certain page of a ledger. What's a ledger? A ledger is just a book of accounts. A ledger may contain a sequence of transactions. A ledger may contain the memory state, which is shared across all the nodes. A ledger may contain land records. It may contain, who has asked for a Uber driver, any of this. Right? Okay, so we're going to abstract all of it. Just think of what is going on at the what is going on in the structure of the blockchain. Okay, how do you propose a new node? To propose a new node, you first include a hash of a previous block. So you include a hash of a previous block, and then you include some transactions. And now, in order for you to propose a valid block, you need to satisfy a puzzle. What is this puzzle? It says the hash of this entire block, which contains of the reference to the previous block, the transactions, and a special string called nonce together satisfy a certain threshold. Okay, so it turns out because of some cryptographic properties of this hash, what you need to do is to try randomly many different strings, and whichever string satisfies this property, if you found a string that satisfies that property, then you have a valid block. So the string is called, the valid string is called nonce, and once you found the right answer, it's called a proof of work. Why is it called a proof of work? It's called proof of work because you have to do some amount of work on an average in order for you to have made a block. And this proof of work is very critical in making Bitcoin work. Why? Because Bitcoin has no node which says that you can participate in Bitcoin or not. Anybody is free to participate. So if you do that, then to secure the network, you need to make sure that they are contributing some resource to make sure that an adversary does not overwhelm the network. And that's done through this proof of work. Okay, so now you have a valid block. Now you can float this block to the entire network. So this is the basic process. The idea is collect the hash of the previous block, put in some transactions, and try to create a random string such that a certain hash property is solved. And with some probability, you will succeed first, and then you can float a block. So that's the basic structure. Throughout the talk, if you have any clarification questions, please stop me immediately. We will take discussions at the end of the talk. Okay, so we now look at the actual process, which is not happening through a single node, but it's a distributed mining. And now you can abstract out the details of mining. Nodes are trying to solve this random puzzle, and whichever one first solved the puzzle, they extend the chain, right? So first chain, somebody made a block, somebody else made a block, and then maybe at a given time, two nodes simultaneously made a block. So there are now two versions of the fourth block. Think of it as I'm trying to construct a ledger page by page. Somebody says, hey, this is page 4. Somebody says, maybe this is page 4. Now you have a split view. Okay, so now what happens is one of the nodes, some nodes may be working on one view of the ledger, one of the chains, and one of this chain, and another node may be working on a different chain. And with some probability, some node will make a block extending one of these chains, and then the protocol says you follow the longest chain. Once this block has been made, since this chain is of length 5, everybody will continue to build on top of this. So some things to observe immediately. The blockchain itself Bitcoin itself only uses basic cryptography, the security of digital signatures, the one-way function property of hashes. But really what is going on here is the construction of a random process. The mining has created a random process. And if you think of what is the length of the longest chain, that's like a Poisson process. It's just a counting process increasing in time. And the protocol is the longest chain protocol. It says, everybody, if you're an honest node, you have to grow on the longest chain. But if you're an adversary, you may not follow the protocol, you may do something else. And the core aspect of the security comes from whatever the adversary does. The honest nodes, as long as they follow the longest chain protocol, the system needs to be secure. Okay, so that's the basic structure of Bitcoin. I will highlight that there is a simple attack on Bitcoin, and then I'll show how people defend against it. Suppose you have a transaction of interest. Let's say somebody gave you a $10,000, and now you give them their car because you saw that, hey, that transaction went into a certain block, and that block is now part of Bitcoin. So you feel very happy, and then you give them the car. They go away, and it turns out in the next 15 minutes, you see the following thing. Somebody, instead of making blocks building on top of your transaction, now has built blocks on a separate chain different from that transaction. And now if you follow the longest chain rule, everybody is going to keep growing on that alternate chain. And now your transaction has gone into the dustbins of history. So nobody knows about it, nobody cares about it, because everybody only cares about the longest chain. So this is called a double spend attack. I spend the money, and then I got the goods, and then now I reverse the longest chain. Okay, so why is it even possible? It's possible because you accepted somebody's transaction as soon as it went into a block. And the basic thing that's happening is blocks that are at the edge of the tree, of the chain, are not that stable because they could be more easily displaced. Blocks that are deeper embedded into the chain are harder to displace. And you should have used it when confirming the transaction. So that's the K-deep confirmation rule, which says that don't confirm a transaction as soon as it makes it into the block. Wait for a few blocks to be built on top of it, K blocks to be built on top of it. Then you can confirm it. So what's going to happen? Why can't the same attack still happen? So for the same attack to still happen, what you need is nodes that are adversarial now need to grow a chain which is longer than this public chain. And unless they control more than 50% of the mining power, it is very difficult for them to do so. This is basically the law of large numbers operating on the blockchain. Okay, and Satoshi Nakamoto in their original table made some calculations seeing what is the reversal probability of a given block, given how deep it's embedded. As you can see, if it's very deeply embedded, k equals 50, you have a very low reversal probability, 10 to the minus 6. If k is 10, then you have like 4% reversal probability. So you would at least want something like k equals 20 to be sure that your block stays with 99.9% probability. Okay, so this is the primary reason why you have high latency in Bitcoin. Why? Because you need not only your transaction to get into a block, but you need some other blocks to be built on top of it in order for you to confirm the transaction. This induces a huge latency. Each block in Bitcoin is mined every 10 minutes. So if you waited for 20 blocks, that is 200 minutes or 3 hours. Okay, so now the obvious fix that one can think of is basically speed up the block mining rate. Mine blocks not once every 10 minutes, maybe mine a block every millisecond. If you do this, this is what will happen. The rate of simultaneous mining. What is simultaneous mining? Different blocks are mined at the same time. The rate of simultaneous mining will go up. If the rate of simultaneous mining goes up, then the problem is you have many different versions of the longest chain, and there is no confirmation of any single block. And even more importantly, the problem is that the adversary, even though the adversary doesn't have more than 50% of the mining power, so here, for example, the adversary only is able to mine 4 blocks, whereas the honest nodes have mined 10 blocks. But still, the adversary is able to mine a longer chain because the adversary's work is coordinated, whereas the honest work is distributed and scattershot. So if you speed up Bitcoin, basically you lose security. And we can do some nice mathematical analysis which shows that the security indeed, the security threshold, which is the fraction of adversarial power, indeed goes to 0 as you keep increasing the mining rate. So that's why in Bitcoin, the mining rate is set conservatively at once every 10 minutes. Okay, so now that we know that there's a latency problem in Bitcoin, many proposals have come trying to improve this feature. However, they all try to change the longest chain structure in some complex ways, and it has turned out that most of them have new attacks on them. And one reason is these protocols have not been proven secure in the most general model, which was proposed by the Bitcoin Backbone Protocol. So here we present our protocol called Prism for solving this latency problem. The joint work with Vivek Bagaria, David Shea, Pramod Vishnath, and Julia Fanti at Carnegie Mellon. Okay, so what's the program? What we're going to do is to take Bitcoin, imagine it's a bike, and you break it down into smaller pieces, and then you reassemble it to be something much more efficient. So this is our program. So let's see how we execute it. Okay, to understand this program, the first thing is we need to have a view on how Bitcoin does things. So here is one thing we observed, which is quite interesting. So if you think about each block in Bitcoin, it is playing 2 distinct roles. What are the distinct roles? The first role is a block is proposing a sequence of transactions. We call it the proposal role. But a block, that block is also voted on by the later blocks. Why do I say they are voted on by later blocks? Because you wait for some number of blocks to be built before confirming it. So you can think of the later blocks as actually voting on your present block. So each block is playing this dual role of itself proposing transactions, as well as being a voter for previous blocks. Okay, so the key problem that we observed is an unfortunate coupling of 2 different parameters. What we want to confirm a block very fast is that the votes should come in very fast. But in Bitcoin, if you increase the voting rate, the only way to increase the voting rate is to increase the block rate. If you increase the block rate, then the rate of proposals, which is the rate of alternative blocks, also goes up. And this leads to forking. So our main idea is to deconstruct or segregate the fundamental roles a given block into two different types of blocks. We call one of them a proposal block. A proposal block proposes distinct pages of the ledger. So here is a proposal for page 1 of the ledger, a page 2, page 3, and so on. And we create different types of blocks for voting. A voter block, basically the only job that it has is to cast votes on what is the correct page of the ledger. A very simple idea is, if you want to know what is page 2 of the ledger, let's say there are 1,000 voter chains. This is a parameter fixed at the beginning of the protocol. If there are 1,000 voter chains, you can have at most 1,000 votes at any given level. And if you want to know who won that level, you go and ask, you take the maximum among all the votes, whichever block got the maximum votes, that is considered the winner. Okay, so why is this latency efficient? This is latency efficient because instead of waiting for votes to come in time, that's what is happening in Bitcoin. So you make a block and then votes are coming in time because new blocks are being added. Here, votes are coming in parallel, in space, so to speak. These 1,000 voter chains, so as soon as you mine a block, within the next 10 seconds, you can have votes on all the 1,000 chains. That means you can immediately confirm the block. So that's the main idea in how we get low latency. We also have another round of decoupling, which segregates it into another type of block called transaction blocks, which I will not talk about. This is for improving the bandwidth performance. Okay, so let's go a little bit slow and try to distill why this really works, because it's a bit mysterious. So let's just take a simple case. You know, there are two possible blocks here, and block 1 got 999 votes, and block 2 got 1 vote, right? So you could potentially confirm block 1. So let's try to understand this very carefully in another example. So let's say for block 3, let's say all the 1,000 voter chains have already voted for this block. Can I immediately confirm this? And how sure am I that the confirmation remains? Remember that each of these chains, 1,000 voter chains, is running basically a longest chain Bitcoin type protocol. So that's why we said we've taken the paths from Bitcoin and then built up a tensorized structure, so to say. So what is going on here is all of these chains have voted on this block. Okay, now can I confirm this block? We can look up Nakamoto's table and see that if a block is embedded 1 deep into the blockchain, then the confirmation probability is maybe 80%. So with 80% probability, we can be sure that this vote will stay in the longest chain. Remember that if there is a fork of the chain, then some other vote could potentially get in instead of this vote. So each vote itself is not guaranteed, it's only probabilistic. But here's the main idea. If you had a vote which is only confirmed with probability 80%, you should not go and accept that transaction in Bitcoin, because with 20% probability, you're going to lose your money. But here is the main thing. There is an action of law of large numbers across space. Suppose you already have 1,000 votes for a given block, and each vote is stable with probability 80%, right? We know that 800 of these votes are going to be stable with very high probability, right? So this is just like you take a weak classifier in machine learning, and you can build a strong classifier using many independent weak classifiers. So that's roughly what is happening. So you can now confirm with 99.999% probability that more than 800 votes will remain on this block. So you can immediately confirm this block. And if somebody tried to create an alternate block and tried to vote on it, it will not garner more than 200 votes. And therefore, the block you confirm remains in the ledger forever. That is the key property that we have in Prism. Okay, so let's understand just one more case to really see what happens in an extreme case of attack. So here is an attack called the balance attack. So what we do here is that the adversary, the adversary here has created two versions of a block. One version says Alice pays Bob $1 million, And the other version says Alice pays Carol $1 million. There's only $1 million with Alice, so only one of these two transactions can make it into the ledger. And the adversary somehow arranges these blocks to be sent at the same time, roughly. So the vote gets roughly split between the two blocks. So one of them garners 501 votes and the other garners 499 votes. Now, again, if we had some little bit protection for each of these votes, can we go and confirm this block with 501 votes? No, you should not do it. Why? Because if you confirm this block with only 501 votes, we know that each vote is only stable with 80% probability. So think of it as like, this is like an election where the margin is very small. So if you appeal, you could potentially, overturn. It's exactly the same thing that each of these longest chains has a potential probability of forking and the vote getting dislodged. So you cannot be sure that the block with 501 votes will remain the leader for all of the future. However, what we can confirm immediately is that one of these two blocks will remain in the ledger forever, because any alternative block can only get at most 200 votes, and existing blocks cannot lose more than 200 votes. That means that you can confirm that one of these blocks remains in the ledger. In information theory, this idea is called list decoding. You decode not to a single element, but to a list of possibilities. Okay, so, and as things go by, as each of these votes gets more and more confirmed, why do votes get more and more confirmed? Because they get embedded deeper and deeper into the ledger. Then you can start confirming one of the two blocks eventually. Okay, so there is a fascinating theory to analyze this problem. And what we showed is essentially three properties: that Prism is secure as long as less than 50% of the compute power is controlled by adversaries, is latency optimal, which means you can confirm as fast as the network allows you to, and also bandwidth optimal, which means you can increase the throughput till the network bandwidth allows you. And there are many ideas from information theory and networking that are useful here to analyze this kind of a system with arbitrary adversarial strategies. We use the idea of typical sets. Typical set is a core concept in information theory, which says that if different, what are the events that happen in a typical execution? So if you execute the protocol typically, honest nodes will produce more blocks than adversaries and so on. So you can try to analyze this kind of thing. And these 1,000 chains, even though the randomness is independent, the adversary could do some manipulation to correlate it, and we have to analyze these things carefully. We saw the idea of list decoding, which is again crucial. And finally, what we call as differential quality of service. What differential quality of service means is honest nodes which propose honest transactions get a better quality of service. They get instant confirmation, whereas dishonest nodes can take much longer for things to get confirmed. So this is a subtle property which I will not go into, but it is indeed, I think, the correct way to allocate service. Okay, so that concludes the theoretical claims on Prism. I'll quickly highlight that some of our collaborators, along with Mohammad Alizadeh and the Systems Research Group at MIT, actually went and implemented this in a open source implementation. And here you see there are two axes for comparison. One is throughput and the other is latency. And beta is the adversarial fraction. So you see here longest chain, which is like Bitcoin, is here. We've also shown another protocol called Algorand. Maybe we can ignore it for now. And you have a Prism showing up on the top. So if you see, the fundamental difference between these protocols in performance is there is a 3 orders of magnitude improvement in throughput, going up all the way from 1,000 transactions, hundreds to thousands of transactions to 100,000 transactions, and also 2 orders of improvement in latency simultaneously. So you get simultaneously better latency. Confirmation happens in 20 seconds rather than 1,000 seconds. And as well as throughput is much better. So our theoretical predictions actually were even beaten in the empirical evaluation. Okay, so let's go back to our scorecard. The scorecard looked at what the various properties are. There was a big problem because your confirmation latency is 3 hours. You cannot wait for a coffee for 3 hours, but maybe 20 seconds is okay. Okay, so the next problem that we're going to address is energy efficiency. So I think somebody raised hand. Blake, please ask if you have a question.
My question was, what about energy efficiency?
Oh, thank you. That's my next part. Thank you, Sreeram. The next problem is energy efficiency. Did our protocol improve energy efficiency? No, it is not worse than Bitcoin, but it's the same as Bitcoin. So, but Bitcoin is no good, taking up Switzerland's energy. So let's see what we can do about it. Okay, so the key idea is we are building a new protocol which is not requiring proof of work. Proof of work is energy inefficient. So instead we use proof of stake. So what does this mean? So instead of nodes trying to prove that they have wasted a certain amount of computation power, they prove that they own a certain number of coins, for example. This is called stake. Stake is how many either coins you own, how many tokens you have, whatever. Okay, so there have been many protocols proposed to try to understand or improve this energy efficiency problem, saying that computation is wastage, whereas if you just have to prove using some cryptographic primitive that you have ownership of a certain tokens, then that is much easier. For those of you who may be concerned that this leads to rich get richer, there is a very similar structure for something called proof of space, where instead of proving that you have wasted a certain amount of compute power, you just show that you have used a certain amount of RAM to store data. So these are based on problems, cryptographic problems, that are guaranteed to require a certain amount of space to execute. But the structure of these protocols are all similar, so I'm going to just talk about proof of stake. Was there a question?
Yes, I was just wondering then, if using this method, how do you initially start mining, since if you start mining, you wouldn't have any Bitcoin in the first place?
That's right. So there are various hybrids proposed. For example, initially you do proof of work till some time, and then you switch to proof of stake. You distribute tokens in the free market. You distribute tokens to people who solve some mathematical problems. The token distribution problem can be segregated from the network maintenance problem. So I think this is only talking about the network maintenance, but great question. Okay, so for example, in proof of space, there is no issue even for token distribution. Anybody can show that they have some excess space in their computer and then participate in the network. Okay, so one core protocol in this, so there are a bunch of protocols, but they all suffer from one problem. We call it the predictability problem. What is the predictability problem? The structure of the protocol goes something like this. You have a block, G, and now there is some randomness embedded in this block. And what these protocols do is they say, if you have a token, if the hash of that token or your public key and this randomness is less than some threshold, then you get to propose a block. So it proposes, it gives a mechanism by which these nodes have an allocation to different times. So now each of these nodes get a slot on when they can propose a block, and then they sequentially propose those blocks to construct the chain. One issue with this kind of structure is that these protocols require long epoch times, and they can be predicted days ahead who the next leaders are going to be. So this is very different from Bitcoin, because in Bitcoin, you don't know who the next block producer is going to be. And as soon as they produce that block, they have no future power in the network. But that structure is not true in these protocols. Okay, so this leads to a bribing problem. So what I'm going to do is to show an alternative, actually very simple proof of stake mechanism, which was the first thing that anybody ever proposed, but it had a serious mathematical problem that we could resolve. So here's the idea. So when you want to propose a new block, you use some randomness from the previous block, which is very fresh. So think of randomness as just the hash of the previous block or something like that, right? So it's just something that depends on the previous block, and it is fresh because the block was mined newly, so you cannot predict what is going to happen ahead of time. Okay, so you put in your transactions, that you always do that. Then instead of looking at trying to generate many strings and seeing one string that satisfies a threshold, all you do is for at each given time, you take your public key. Let's say you have a certain public key and you hash that public key and that randomness and the time is less than a threshold, then immediately you are allowed to propose a block. So this now becomes proof of stake. So all you've done is say that instead of trying random strings, you just try your own public key at that time. And it's a very simple protocol. And so it's not like we had to come up with this protocol. This protocol is already there. But the main issue is that this protocol has a serious attack called the nothing at stake attack. What is the nothing at stake attack? If there are multiple chains, here there is this chain and this chain, right? Normally, the protocol is that the adversaries, so all honest nodes should choose the longest chain. That remains the same. However, the adversaries also had to choose one of the chains. They could not say earlier in proof of work that I'm going to try to mine a block here and here. Because if they try to mine a block here and here, that means they need to expend computational power here and computational power here, which means they have to split their computational power because it's a race in time to see who gets the next block. However, in proof of stake, there is no such issue because you're not expending any physical resource. Just checking whether your public key's hash is less than a threshold takes a microsecond. So adversaries don't have any reason to stick only to one chain. So this is called the nothing at stake attack. This was the reason this protocol, even though it was proposed like 5 years back, nobody takes it seriously because it has this issue. Okay, so here is what an adversary can do to exploit this there's nothing at stake attack. Suppose there's a block and I wanted to mine a private fork which is longer than the public chain, and then therefore overturn the longest chain. Instead of only focusing on mining a single chain, I could now mine, for example, once you have this block, I try to mine multiple blocks on top of this block. And once you have this block, you try to mine multiple blocks on this block and so on. So what happens is over time, the adversary can mine an exponential number of blocks, far greater than the blocks mined by honest nodes, because honest nodes only mine on the longest chain. That's the protocol, they follow it. Whereas the adversary has no obligation to follow the protocol and creates a really huge number of blocks. Okay, so the key question is this, when is this secure? And we can try to analyze how this works by first looking at the honest growth rate. Is if your chain is growing at rate lambda and 1 minus beta of the power is controlled by honest nodes, the longest chain is growing at least by lambda times 1 minus beta. And the question is, how fast does this exponentially growing tree grow? A really nice result, which shows that this actually grows exactly at a rate E, factor E greater than the original power. So which means that as long as the honest rate is greater than the adversarial growth rate, then the protocol is potentially secure. In fact, what it actually shows is that if your adversary ratio is greater than 1 over 1 plus E, if the adversary ratio is greater than 1 over 1 plus E, then the protocol is not secure. It does not show. So this analysis is already done in one of the existing papers. However, it does not show that if the threshold is, if the adversarial stake is less than this number, 1 over 1 plus C, the protocol is secure. Because this is only one attack that was analyzed, and the space of attacks is actually quite complicated. Okay, so what can we say here? So we have a new approach, which we call as adversary-proof convergence. So the basic idea is you take all the honest blocks, which are shown in blue, and the adversary can grow these infinitely forking trees out of these honest blocks. And you say that the honest chain will win the race if there is a block, which we call as a refresh block. A refresh block is one which, due to a stochastic event, so it's a stochastic event which says that a block is a refresh block. A block is a refresh block if none of the previous trees can ever overtake this block. And now you have to analyze not only one tree, but many, many trees growing in parallel and understand whether they can catch up to this public block. And to do this, we have to, so each of these trees is actually what is called a branching random walk, which was studied in stochastic processes. And we try to utilize some of that theory of branching random walks and large deviations of these branching random walks to actually show that indeed the threshold is correct. So as long as the adversary ratio is less than 1 over 1 plus e, 1 over 1 plus e is like 27%. As long as the adversary controls less than 27% of the stake, then this protocol is indeed secure. Okay, so you may ask, in the proof of work case, the threshold was 1/2, whereas here the threshold is 1 over 1 plus e. Is it a fundamental thing? Can you actually propose something that takes it all the way to 1 over 1 plus 1 over 2? And there are existing attempts to try to do this, and we found that they are vulnerable to a certain class of attacks because they're not proven secure in the general model. So we came up with a new protocol, so what is happening here is that the randomness at each level is totally independent, which leads to a highly forking tree. So instead, we create a certain correlation in the randomness. We call it C correlation. As you improve the correlation, then the forking goes down. So you can calculate the threshold, and for example, what we can show is even with, say, C equals 10, so you use a certain parameter C for correlation, what we can show is you can already achieve like security of 0.45 with very small prediction. Okay, so that concludes the energy efficiency part of the discussion. You do not need to do any mining, so this protocol does not waste the electricity of Switzerland. Okay, any clarification questions on this before I move on? The final aspect that we want to talk about is throughput. Even though the latency is bad and the energy efficiency is bad, the throughput is also bad in Bitcoin. And the reason is there is no scaling. As you get more and more nodes, the ability of the network to process transactions does not grow up. So this has been a kind of a project with many collaborators. Two particular things called Polyshard and coded Merkle tree came out of this. Okay, so let me explain what this is. So if you look at Bitcoin, it follows full replication. What do you mean by full replication? Every node needs to replicate the entire blockchain, needs to store the entire blockchain, needs to compute every single transaction is valid, and that's how Bitcoin works. So you get absolutely no scaling, no performance scaling. As you get more nodes, does the throughput increase? No. But you get high security. What do I mean? As you get more nodes, unless a 50% fraction of these nodes are corrupt, your protocol is secure. So the security is scaling, but performance is not scaling. Okay, so there is a proposal called sharding. Sharding is an idea in databases and has been absorbed into blockchain. And the idea is very simple. Why are all these nodes maintaining the same ledger? Why not sort them into groups? Each group maintains distinct aspects of the ledger. There's a blue ledger maintained by the first 3 nodes, a red ledger maintained by the next 3 nodes, and a black ledger maintained by the last 4 nodes. Seems like a reasonable idea. This is called sharding. Okay? Each of these groups is going to be called a shard. There's a blue shard, a red shard, and a black shard. So they're all maintaining distinct things. Okay, seems like a reasonable idea. You do get performance scaling, right? Because if you make the size of each group small, as you get more and more nodes, you get more and more performance. More transactions executed in parallel, more storage, everything. However, there is a significant issue. The issue is if a majority of nodes in any given group is corrupt. Let's say there are only 3 nodes in this group. If 2 nodes are corrupt, then you have no security. Okay. So how do they deal with it? They deal with it by something called allocation. What is allocation? Nodes are allocated randomly into shards. So take the nodes and then randomly sort them into shards. What that does is to make sure that the proportion of adversary in a group is representative of the proportion in the population. Okay. So you take the population of all the nodes, let's say 30% are adversaries. If you choose randomly 100 nodes from this entire population, maybe 35 of them are adversary, but not more than that. So that's the idea. So people have been trying to do sharding using this basic idea. However, the problem is, bribing or corruption is adaptive. Once you see that, I have $1 million in blue money, and I know only these 3 nodes are maintaining it, even though while they were allocated to this shard, they were all honest, I will just go and bribe these 3 nodes. So it seems very, very simple to corrupt it post facto. After the allocation has been done, now you can go and corrupt whichever ones actually really matter to you. So what you get is under this adaptive adversary model. The adversary is adaptive to the allocation. It sees the allocation and then corrupts. You do not get high security. You get very low security. Any group needs to be majority honest, rather than the entire network seems to be majority honest. So there seems to be a fundamental tension between security and scalability. Either you get no scaling and high security, or high scaling and low security. Okay. Okay, so this is not just on the sideline. There are many academic works trying to understand this, many multi-billion-dollar projects just trying to build these sharding systems. Yet none of them are fully secure against adaptive adversaries. And this has been one of the reasons for many of them hesitating to go live. Okay, so we will now state a very simple algorithm. This algorithm itself is not the hard part. So what you do is let nodes belong to one of these K shards. So there are K shards, and nodes belong to one of these K shards. But also you maintain a common shard. So nodes mine blocks on each of the shards, let's say shard A, shard B, shard C, and they also mine blocks in the common shard. Now, what is the data that goes in the common shard is just the hash of the blocks that got mined in these different shards. So, the common shard basically gets blocks which refer to hashes of the blocks in these different shards. So if you wanted to read out what the shard C was, you just go and see what are all the hashes of shard C blocks that are in the blockchain. That gives you an order, and then now you can read out the shard C ledger. So this idea is very simple, and it's immediate that this is safe against adaptive adversaries. Why is it safe against adaptive adversaries? Because it doesn't matter what fraction of adversary controls each shard. All that matters is who controls what fraction. So the order of the shard is dependent only on the order as written in the common shard. And since the order in the common shard is secure as long as total mining power, 50% is honest, so you do get security. However, there is a catch. The catch is that an adaptive adversary now, instead of spoiling security, can spoil throughput. What do I mean by it? Let's look at the 3 shards, A, B, and C. And let's say the honest nodes. So here I'm making honest nodes look green, right? Green nodes are honest, and red nodes are adversarial nodes, right? The honest nodes are equally allocated, roughly, and the adversaries are also equally allocated. Then everything seems to work. However, what happens is adversaries can now congregate. They all go and congregate onto shard 1. So this is an adaptive adversary. And what is going to happen to shard 1 is most of the blocks produced in shard 1 are filled with red, which means they're all like malicious blocks. These malicious blocks, for example, can censor transactions from honest nodes. They can include invalid transactions, whatever. Okay. So this is a risky thing. So your adversary cannot spoil safety. Safety means a transaction that's confirmed remains confirmed. This, however, the adversary can suppress throughput significantly. Okay, so that's the problem. How do we solve it? So here's the basic idea, and it's a really interesting idea, is you chase the adversary. So what does it mean? If you see that, for example, in the previous picture, the adversaries have congregated on shard 1, then maybe even if the honest nodes also go and congregate on shard 1, then you can balance it out. Okay, so let's see what the protocol is. You see that the adversary is congregated into shard 1. Now, the honest nodes respond by also congregating, right? These are all probabilistic events. I'm just showing them nicely. And so now what happens is now you still have a majority of honest users in shard 1, and then they start producing blocks. So the throughput now, instead of being all blocks being honest, you get like 3/4 of the blocks being honest, depending on the fraction of adversarial and honest nodes. So we call this dynamic self-allocation, which is you look at the current state of honest and adversarial users in various shards and then decide where to go. So just a little bit of math for those of you who may be interested, just 1 minute, is, so suppose in shard I, the total honest power is gamma I, and the adversarial power is beta I. The rate that we get is gamma I by gamma I plus beta I, right? This is the fraction of honest power. So that controls the rate in that shard. Okay, if you knew beta I, right? If you knew beta I, then one simple strategy is make gamma I equals beta I. If you make gamma I of t equals beta I of t, then you can get rate 1/2, which is almost as good as, so we call this the oracle bound. The oracle bound is if you knew the adversarial allocation a priori, then you will also allocate yourself proportional to the adversary. However, you do not know the adversarial allocation a priori, but you know the history of adversarial allocation. And somehow you allocate yourself not based on the current fraction of adversary, but based on some previous epoch, what the adversary's fraction was. So we call this proportional rotation. And you can ask, suppose you do proportional rotation, what is the throughput? So the term you see here is the throughput at a given time. This is the average throughput over time. This is the average throughput over time of shard I, and the min over I is the throughput of the worst shard. And you're looking at whatever the adversary does, you should be guaranteeing a certain rate. So that's what is called psi of k. So that's where the full power of the adversary comes in this game. So we have a nice theorem characterizing what this psi of k is for this policy, is between 1 over log k and 1 over log k or log k. So it's very close to 1 over log k. And we point out that if you did static allocation, what is static allocation? Static allocation is gamma I of t is equally allocated to the various shards. So gamma I of t is 1 over k. And in a worst case shard, beta I of t can be 1/2 because everybody can congregate there. So what that means is your throughput is very, very small in static allocation. However, this dynamic allocation improves it from 1 over k to 1 over log k. For example, if k is 100,000, then 1 over k is 10 to the minus 5, whereas 1 over log k is 1 over 5. Okay, so that is the dynamic self-allocation. And what we can see is, even though this is very good, it's still a little bit far from the optimal one. If you knew what the adversary did, you could get rate 1/2. And we were stuck with this problem for a while till we found a classic work of Blackwell, who is a distinguished probabilist who worked on the dynamic games problem. And the strategy is actually really simple. So what you do is you allocate your honest power dependent on how far you are from your target throughput. Let's say your target throughput is 1/2. Now, if you're far from one half, then you allocate more power to that shard. So it's a very interesting strategy and beautiful theorem that we can basically borrow from Blackwell. Shows that, essentially the average rate of any shard converges to one half for any adversarial strategy. So this is because, they analyze these dynamic games. And what we find here is a stunning result that if you did adaptive adversary, but you followed with dynamic allocation, that is as good as if the adversary were static. So you can basically approach the oracle bound in this problem. So this Blackwell approachability and related versions have found applications in many areas in boosting, in online convex optimization, in online learning, many different areas, in dynamic game theory, of course. And we find this is a very nice use of this general framework.
Sorry, just a question.
Yes.
So that previous equation, can we just see it as a proportional controller?
Yes. Yes.
Okay.
So this is control against adversaries. Exactly. So it's what you would call as, some version of robust control, or control not with noise, but with adversarial action.
Okay.
So this Blackwell's theory has also found many uses in control theory. So
thank you.
Yeah, thanks for the question. So what we find is this protocol, Trifecta, which builds on this core dynamic allocation principle, but also need other ideas, for example, using codes for distributing data and so on, can actually achieve near linear throughput with full security against adaptive adversaries. So we can do some simulations and try to understand what the throughput is. And as I said, you can only do simulations for some adversarial strategies. You need the full power of the theorem to show that it works for arbitrary strategies. So here you see that I'm plotting over time, the throughput of the shard, which has the lowest throughput. And these are some interesting adversarial strategies we thought of. And you can see that, the shard throughput converges to a half in these different settings. The dynamics is very interesting, actually, endlessly fascinating. For example, if you see here, this is actually the two axes now are instantaneous throughput of, or the average throughput of shard 1 and shard 2. And you see that, as the adversary is pushing it around, the honest nodes are pushing it around, has this fractal-like behavior, trying to push it all the way to one half. Different strategies have different plots, but all of them exhibit similar behavior, confirming the theory. Okay, so what we see here is that the throughput problem can be redeemed. And indeed, we see that our protocol has linearly scaling throughput with the number of nodes. And in our implementations, we can actually hit 250,000 transactions per second. And I'm going to just briefly show you an animation. So here we go. Okay, so here is an animation of putting everything together. We had three ideas: the Prism, which improved the latency. We have the idea of proof of stake, which replaces proof of work. And finally, we have an idea which says that you can do this sharding in this certain way. So now I'm going to show you our protocol, which does all of this. Okay, so here is the protocol. So what you see here is nodes across the world, they mine different blocks. The blocks get sorted into different types. And there is a proposal chain. There is a voting chain on the right. Everybody maintains the proposal chain and the voter chain. And nodes in distinct shards only, so on the left side, you see blocks of different colors. And if you are interested in only a certain shard, you only maintain that shard. So for example, if I'm interested only in the purple portion of the ledger, I only maintain the purple portion of the ledger. And so each node now maintains its own shard, on the left side, its own shard, the purple shard. But every node maintains the green and the purple blocks, and the green and the blue blocks, which is the proposal and the voter chain, thus pooling security across the different shards, but giving efficiency as though you're only maintaining your own shard. So with that, let me go back to my talk. That essentially puts all of these different aspects together into a single protocol. And I want to highlight that ideas from information theory, networks, communications, and control have a significant role in solving the scalability problem of blockchains. And finally, I would like to thank my students in the information theory lab, as well as my many collaborators on different projects here at. Thank you.
Thank you very much. We can use the clapping icon to applaud. Okay, and are there any questions? Please raise your hand. Yeah, there's a lot of applause. I'll give it a second to see if there are any questions. I believe there was one question in the chat window from earlier. Let's see.
Okay.
Although it may have been Sudipto, did you still have a question?
Oh, Scott Hart.
Yeah, so I couldn't follow one thing, like the threshold when you use the proof of stake was 1/1 plus E, and the original Nakamoto protocol was 50%. So just the proof of stake, what is the maximum it could be reached? Is it this dynamic?
Oh, yeah. So I briefly mentioned that you could actually increase all the way from 1/1 plus E to 1/2 by using this thing called correlation, C correlation. So I didn't go into details about it, but there is a version of our protocol which actually goes as close to 1/2 as you want.
Okay, thank you.
Scott,
question? Yeah, question by Scott.
So I may have missed this, but how do you identify the adversaries, or does it not matter that you identify an adversary?
That's really the beautiful thing, that the security of this protocol does not rely on identifying the adversaries. You don't need to know who they are. What you know is honest nodes will be following the protocol that you give them, right? Think of putting out a code, right? So there is a Bitcoin code base, you can just download the code. The honest nodes, if you want to participate in the Bitcoin, you just download the Bitcoin code and run it. Whereas the adversarial nodes will take the code and manipulate it to whatever they want. And so you don't know who the adversaries are. You can't track them. You can't penalize them in this permissionless world. However, the guarantees really show that even in this world, you can actually guarantee security.
And if you have non-coordinated adversaries, so that you might have a bunch of different groups that are independently adversaries, do they act as if they're honest brokers against other people or not?
That's a great question. So there is one dimension that I have not addressed at all in this talk, but it's a very important dimension in the real deployment of Bitcoin, is incentives. Why are these people really doing this, right? What is their incentive? Why are they following this? And that's a really long discussion, very interesting and fascinating stuff. But at the moment, our theoretical guarantees assume that the total fraction of adversaries is less than 50%. There are incentive analysis which says that as long as any coalition is less than 50%, that is sufficient. That really addresses the question that you're asking. But that is true only in the incentive world. Here we are assuming that some nodes follow protocol, they're just going to follow everything. Other nodes can do arbitrary things. How they coordinate is up to them, and we cannot control that.
Well, thank you.
I have a quick question. The beta I, which was the adversarial rate, do you have to make some assumption on that? So for example, adversary
you have to
can
assume
change
that the
fast.
summation of beta I is less than overall I, the total sum is less than half. So the same assumption, the recurrent assumption through the whole thing is the total adversaries is less than half. In the sharding part, the thing that could have happened is even though the total adversary is less than half, they could all congregate onto a given shard. That's the effect that we're trying to protect against.
And you are minimizing over all beta I, just subject to the constraint.
Exactly. All beta I is subject to the sum constraint. And the beta I goes after. So it has more power because first you decide gamma I and then you decide beta I. So the adversary will look at you and then hit you where it hurts the most. And what we show is that, and the adversary has full knowledge of your protocol. Even after all of this, you can show that an adaptive adversary does not have any power more than being a static adversary. So this was a surprising result. There's one thing that it does hurt, which is latency, which is you may have some stretches of time where you had a bad run, but over long runs, you can still converge. So, and exactly what this convergence rate is, we have some bounds, but you can potentially improve them significantly.
Yeah, an interesting connection to online budgeted allocation problems. Against adversarial unseen future.
Exactly. And also to this bandit problems, right? So adversarial bandits. So that's again closely related, the multiplicative weights and its connection to boosting and so on. So there are many variations on this theme, but I think Blackwell had one of the really nice formulations in this vector games.
Yeah, definitely interesting connections to explore there. So, okay, let me see. Any other questions? One more question in the chat. Let's see. Sudipto has a follow-up question. So let's, okay, go ahead, and this would be the last.
Go on, Sudipto.
Sorry, so I posted the question. So in the various protocols, some kind of attack was considered, like balance attack or double-sided attack. But what if some other type of attack comes? Is it like the protocols or the theory immune to any possible attack, or only?
Excellent question. So there is a modeling of what is the space of all possible attacks, and in our analysis, which I think is the most general that we know of, what we do is we say that the adversary can mine blocks anywhere. Right? So where to mine. Second, the adversary can release blocks whenever they want. So this is when to release. 3, the adversary can put whatever content they want into the blocks. So this is what to put. So where to mine, when to release, what to put, you have a really infinite state space there because all of these can be dynamic and responsive to the current state of the protocol. Furthermore, we assume that the adversary controls packet deliveries in the network. So this is the timing model. So when you send a packet through the network, everybody receives it within a time delta. But the adversary can arrange the ordering of these events in order to create maximum confusion, as long as the delivery is still guaranteed within delta. So this is the adversarial network model. So we take the adversarial network model, adversarial mining model, adversarial release model, adversarial transaction model, and all of these results hold against this complex events. There could be something, right? Like if beyond all of this, for example, you implemented, there is in your blockchain, and then there is a denial of service attack. So it's not modeled here. And those are attacks at different layers that one needs to consider in implementation. And we know by, for example, Radha has worked a lot on network security. We have problems where, theoretically you can show everything is secure, but in the network implementation, there can be significant vulnerabilities. So those also need to be considered in the implementation.
Okay, thank you very much again. Great talk. And thanks everyone. We'll end the colloquium. See you all next week.